let's find out how to configure this structure so that the heat current, obviously entering through this surface, proceeds the easiest. That means with this smaller and smaller temperature difference from the hot end to the cold end. See that? There's a heat current which escapes as Q over 2 here and another Q over 2 here. And so the focus will be on the thermal resistance, which is delta T divided by Q. The objective is to make this thing smaller by morphing the flow architecture. But listen, obviously, to make this thing smaller and smaller, first you have to reach in your pocket and buy a material that's a better and better heat conductor. So the material has a thermal conductivity K, which is considered fixed or known. Speaking of what you pay for, you have a certain amount of material, and that's the volume of solid. So that volume is a constraint, namely what, L1, D1, and then this other dimension called width, W, plus twice the volume of one of the branches, L2, D2, and W. It's the same analysis as the one we've done for the flow through a branching stream of water. Instead of delta T, we had delta P for pressure difference. And instead of Q, we had m dot for the mass flow rate. See that? And back then, we recognized that the overall pressure difference is the sum of the two pressure drops, one along the big and the other drop along one of the branches. It's the same here, that what we would like to decrease is delta T1 plus delta T2, where delta T1 is the temperature difference here from left to right, and delta T2 is the remainder. Now, heat transfer, the study of it is the simplest, and the simplest of all those is in the realm of solid body conduction. There's a formula that is known as the Fourier law, but it's actually not a law. It is a definition of thermal conductivity. It is written this way. For the delta T1, the Q that enters from the left is equal to a constant called K, and then the cross-sectional area of that's pierced by the flow, namely D1W, and then the temperature difference divided by the path length, which is L1. In some textbooks, this is written as A, the A that's pierced by Q. Here is in our case, never mind. You get the idea. This thing that's behind the drawing is that rectangle D1W. And the same formula applies to one of the branches, namely half of Q is equal to conductivity times the cross-section shown here, which is D2W, and then delta T2 over L2. Easy. Actually, can't think of anything easier. So you have the two expressions. By the way, why is the Fourier law not a law? It is the definition of this conductivity, because you can measure both the temperature difference and the heat current, and then divide them and find the cross-sectional area, and then find the thermoconductivity. Thermoconductivity, temperature difference, and heat flow, that's a stream where heating accumulated, that's the stuff of caloric theory. So these people who invented heat transfer came from caloric theory, a science of the 1700s. How did they measure temperature difference? With thermometers. Thermometry, which lives to this day, is the good hand of caloric theory. Oh, and conductivity is one of the good words of caloric theory. Heat itself, calorie in French is caloric theory. Chaleur is the word in French for that. How did they measure heating or amount of heat? Think about it. I mean, this is 1700s. They had not much. You saw paintings of these people, many of them in places like Belgium and Holland and Sweden, wearing these heavy coats and playing with flames. And yes, they measured the amount of heat by counting the number of candles that were melted by that exposure, so by the exposure to that heating. So they measured caloric by weighing the wax. They're not stupid. They really did it. Okay, fine. So now you know where conductivity comes. Same with viscosity. Viscosity is also the same sort of thing. It's defined by Newton's law of friction. Forget that. Newton knew about measuring the force and measuring the speed, and then dividing the two, meaning having to do with movement at the surface, interface. Then, as they say in the language across the channel, voila, mu, the viscosity. These things, every little thing has a history, which is sometimes quite funny. All right, obviously, I have the delta T1 to substitute here and the delta T2 to put here. I turn the crank. I'm not going to waste your time. And I obtain this expression, delta T, which looks like this. So delta T, all of it, turns out to be Q over KW. And then a group that depends on the configuration, which is really the object of the game. Here you see what doesn't change. What doesn't change is the front factor. So this thing here is constant. The Q is given. Hey, KW doesn't mean kilowatt. It means conductivity times width. And anyway, the rest is the configuration, how to make the drawing. Well, there are 4 variables, but some of them are not varying independently. So we have this constraint meaning we would like to minimize what's in the square brackets subject to one constraint. Now we know about the method of Lagrange with the undetermined coefficient called lambda. So we invoke that. We construct an aggregate function that is the sum linear combination of this group and then the constraint. And so that group is L1 over D1 plus 1/2 L2 over D2. And then the constraint would be multiplied by lambda. Now, the constraint is, you see here on the right-hand side, where W is a constant. So that means that what really matters is the L1 D1 plus 2 L2 D2. L1 D1 plus 2 L2 D2. And you know now, you know more than the technique. You know the technique begins with two steps. In the first step, you assume that the lengths are known, and then you vary only the thicknesses. And by the way, and you vary the thicknesses because a few lectures ago, when we did this problem for fluid flow, the result that came out was the ratio, meaning the recommended ratio of one thickness divided by the other. So the fluid flow, as in blood flow, the result was D1 over D2, 2 to power 1/3. So what we're chasing in this analysis is the corresponding result for conduction through a bifurcation. And it comes out the same way as for fluid flow, but the result will be different. It comes from taking the derivative of phi with each of those thicknesses. So that, and then d phi d2 equals 0. Turns out it's easy to do these things clearly. Versus d1, you have minus L1 d1 squared plus lambda L1. And then from the second one, you have minus L2 twice d2 squared plus lambda, and then 2 L2, in which, of course, L1 and L2 drop out. And you have two estimates for lambda, therefore you eliminate lambda. Those estimates being d1, 1 over d1 squared must be the same as 1 over 4 d2 squared, which means that the result is d1 over d2 equals 2. It is almost what I drew here, meaning that the original thickness branches into, the thickness of the branch is half the original thickness. The other way to say is that the thickness of the conducting blade is conserved at the branching or at the pairing. So thickness is conserved. at bifurcation. Amazing. This comes from 200 years ago when people knew how to describe, I'm not sure they've done this problem back then, but how to describe this invisible flow called heat transfer. But the idea of something being conserved at the branching is much older. Yeah. Take a guess. Whose idea was it? When in doubt, say Da Vinci. Here he is. Okay. Da Vinci had the idea, because he kept looking around, that in the structure of the tree, which really means wood structure. So here's the trunk, and then the branch. The cross-section of the trunk, call it A1, equals the cross-section of the branch, A2, and A3. On the argument that what is conserved at the branching is the number of fibers. In fact, if you look at if you haven't done this, look around. There are trees everywhere. You see from the outside, you see that what was a fiber here continues along the branch. The branch is, looks like an armpit that's not a crack. And yes, it looks like what was flowing from, because water flows from underneath, continues here. And then the rest of it continues upward. Well, it turns out that it is not true that A1 equals A2 plus A3. Meaning true in an argument about history, but not if you start measuring these cross sections. And the reason is that the living tree is a flow system. Water is flowing upward, but it is also a structure with beams in bending because of the wind. And the design that's both good for water flow and stiff to remain vertical in the wind ends up violating this idea. Not violating, but proving it incorrect. But I have not worked on this, so maybe, remind me, make a note. It would be something to think about together. All right. Now, so this result is different than this one. For one thing, 2 is almost twice as big as 2 to the power 1/3. But what about the ratio of these lengths, L1 and L2? That is the second part of the problem, which I did not sketch on the blackboard. You can figure out the L1 and L2 if somebody tells you something about the size of the page or the shape of the page on which this drawing belongs. Is it a rectangle, or are these 3 points, 1, 2, 3, on a circle? It shows you that there's a bundle of problems in this first look at it, which is what I presented on the blackboard. Okay?